All right, we're going to talk about Chapter 3, Lesson 1. We're going to be working on solving equations, systems of equations by graphing. So what we're going to learn is we're going to learn how to solve a systems of linear equations by graphing, and then we're going to determine whether the system is either linear, whether a linear system is either consistent and independent, consistent and dependent, or inconsistent. So some of the vocabulary to keep in mind is what is a system of equations? What does it mean to be consistent? What does it mean to be inconsistent? What does it mean to be independent? What does it mean to be dependent? So how can a system of equations be used to predict sales? So since 1999, the growth of in-store sales of creations by Kathy can be modeled by this equation, y equals 4.2x plus 29. And the growth of her online sales can be modeled by y equals 7.5x plus 9.3, where x represents the number of years since 1999 and y represents the amount of sales in thousands of dollars. The equations are called a system of equations because two equations talking about the same system, right? Talking about the same thing. So if I were to look at these two equations on a graph, they would look something like this. Here's the line for her in-store sales, y equals 4.2x plus 29. Here is the line that represents the equation y equals 7.5x plus 9.3, which is her online sales. And if you can see, although her in-store sales are actually higher at the beginning, as years go on, her in-store sales continue to climb, but not quite as fast as her online sales. Even when they started lower, eventually are climbing at a higher rate. So we're going to talk about graphing systems of equations. So a system of equations is two or more equations with the same variables. To solve the system of equations, we're going to find the ordered pair that satisfies all of the equations. Basically, we're going to find that ordered pair that exists on both equations, on both lines. One way to do this is to graph the equations on the same coordinate plane, and that point of intersection represents the solution, because that point where they cross would represent where the only x and y coordinate that satisfies both equations, that satisfies both lines. So let's look at this. We're going to solve by graphing. So here it says solve the system of equations by graphing, and they give us two equations, 2x plus y equals 5 and x minus y equals 1. So in order to graph this, I could write each equation in slope-intercept form, right? Y equals mx plus b makes it really easy to graph because I can see the slope, I can see the y-intercept, pretty easy to put on a coordinate grid. So let's take the first equation, 2x plus y equals 5. If I were to solve it for y, right, I would just minus 2x from both sides, and it would give me y equals negative 2x plus 5, right? So now I can see that my slope is negative 2, and my y-intercept is 5. Let's take the second equation. Again, all I have to do is solve for y. So I would subtract x from both sides and then probably multiply or divide both sides by negative 1. And it gives me this equation, y equals x minus 1. Okay, all I did to get from here to here was solve the equation for y, get y all by itself. You guys have had plenty of practice solving equations, but if you need a reminder, please feel free to ask. So now I can go ahead and graph them on a coordinate grid. So again, I would have taken this information right here, right? So y-intercept of positive 5 and a slope of negative 2, down 2 over 1, down 2 over 1, down 2 over 1. And then this line, I could have taken it from this equation here. Again, positive 1 slope, negative 1 y-intercept. So I start at the y-intercept with negative 1, up 1 over 1, up 1 over 1. That would make this line. So once I have my two lines, my solution occurs where these two lines exist, right? These two lines exist at one point at the same time. And that is the point 2, 1, 2 to the right, up 1. This is the only point that exists on both lines, which means it's the only x and y coordinate that's going to make both of these equations work. So for this graph, it appears to intersect at 2, 1. So that would be my solution to this problem. So when you're asked to graph, solve by graphing, you have to graph each equation, right? Graph each line. And your solution, the only x and y coordinate that works for both equations is where they meet, where they cross, where they intersect. And for this instance, it is at the point 2, 1. Let's look at another example here. Oh, sorry. Before we move on to another example. So once we have our answer, right, we have our answer of 2, 1, we can go ahead and we can check it. Well, is this actually the answer? Does it actually work in both equations? And the way that you check it is by substituting those x and y coordinates into the equation. So let's look at the first equation. Here I have 2x plus y equals 5. Again, if it crosses at 2, 1, I'm going to substitute 2 in for x and 1 in for y. And then I'm going to see if this equation actually is true at that point. 2 times 2 is 4. 4 plus 1 is 5. So yeah, 5 equals 5. It checks out. Let's check it in the second equation. Again, my x coordinate is 2. My y coordinate is 1. 2 minus 1 is 1. Does 1 equal 1? Yeah, it checks out. So it worked in both equations, which means my solution is in fact 2, 1. Okay? That means that I did everything correctly. So system of equations are used in business to determine the break-even point. The break-even point is the point at which the income equals the cost. If a business is operating at a break-even point, it is neither making money nor losing money. So let's look at our initial example from the beginning of this lesson. This was, again, the in-store sales, and this was the online sales. So at the beginning, in-store sales were more than online sales. But as you can see, there was a point right here where online sales were greater than in-store sales, right? So if I said, where is the break-even point? You could point to there, right? To that point right there. That is the break-even point. That is where they both were equal to each other, right? That is where both online and in-store sales were the same. So let's look at a break-even point analysis. So here we have a problem. It says Travis and his band are planning to record their first CD. The initial startup cost is $1,500, and each CD will cost $4 to produce. They plan to sell their CDs for $10 each. How many CDs must the band sell before they make a profit? So let's go ahead and let X be the number of CDs. We'll let Y be the number of dollars. And basically what we're going to do is we're going to write two equations. One, we're going to write for the cost. And so if Y is the cost in dollars, right? That's going to be $4 times the number of CDs X, right? Plus the startup cost, $1,500. So this equation represents how much it's going to cost them for every single CD they produce. Let's go ahead and look at the money they make now. So again, Y is going to be dollars, and this is now going to be the income, how much money they make, is $10 times the number of CDs, right? Because now they're just making $10 for every CD they sell, their income. So let's go ahead and look at this on a graph. If I were to graph these, it would be Y equals 10x would look something like this. Y equals 4x plus 1,500 will look like this. And as you can see, again, their income steadily grows, but their cost starts higher, but doesn't grow as fast, right? So here is their cost. So their costs go up with the more CDs they make, but their income also increases with the more CDs they make. So down here, the cost of these CDs, like if they only made 100 CDs, if they made 100 CDs and sold 100 CDs, their cost would be more than their income. Where over here, you can see that they are both even. This is what would be their break-even point, right? Where they intersect. And then after this break-even point, their income is higher than their cost. So if they were a band and they wanted to make money, they would be looking to be selling more than 250 CDs because then they start making money. Less than 250 CDs, they're not making money, right? It's their cost is higher than their income. So let's learn about classifying systems of equations. Graphs of systems of linear equations may be intersecting lines, they can be parallel lines, or they can be the exact same line. A system of equations is consistent if it has at least one solution, and inconsistent if it has no solutions. A consistent system can be independent if it has exactly one solution, or dependent if it has infinitely many solutions. So let me show you what that looks like. This would be an example of a consistent and independent system, right? Because here I have my two lines, and their solution would be at this one point where they cross, right? So if you have intersecting lines with one solution, that is what's known as consistent and independent. Now, there are times when the two equations you're given, even if they look different, when you simplify them, make the exact same line. And so this is still consistent because it does have answers, but the two lines are literally right on top of each other. So they're actually dependent on each other. So this would be known as consistent and dependent. And again, this occurs when your two equations make the exact same line, which would actually give you infinitely many solutions because every point on one line would work in one equation works for the other equation as well. So again, these are your two consistent systems, independent if you only have one solution, dependent if you have infinitely many solutions because they're the exact same line. And then the third scenario is if it's inconsistent. Inconsistent means the two lines are parallel and never cross. And if two lines are parallel and never cross, they have no solution because a solution occurs where the two lines intersect or touch. And these two lines never intersect, never touch, therefore have no solution. So again, consistent and independent, one solution. Consistent and dependent, infinitely many solutions because they're the same line. And inconsistent is no solutions because they don't ever touch because they're parallel. Let's talk about an example where that could occur. So graph the system of equations and describe it as consistent and independent, consistent and dependent, or inconsistent. Again, going back to the three scenarios that we just talked about. So let's go ahead and take these equations and let's graph them. So again, I'm going to write each equation in slope-intercept form. So here again, all I'm going to do is solve it for y. So I would minus x from both sides and multiply both sides by 2. And it gives me this equation right here. Y equals negative 2x plus 10. And let's take the second equation. Again, solving for y, I'm going to add 2x to both sides and then divide by 3, which gives me y equals 2/3 x plus 2. So now that I have my two equations in slope-intercept form, again, makes it very easy to solve. Slope, y-intercept, slope, y-intercept. And if I put them on a graph, they would look like this, okay? Again, this line right here with a slope of negative 2 and a y-intercept of 10 makes this line. And this one right here with a y-intercept of 2 and a slope of 2/3, right? Rise 2, run 3, would make this line. And so now I can see that these two lines intersect at the point 3, 4. So since it has one solution, right, and they do intersect because they have one solution, this is what's known as consistent and independent, right? Consistent and independent is when they cross at one point, has one solution. Let's look at another example. So here's an example where I have a equation. So it says graph a system of equations and describe it as consistent and independent, consistent and dependent, or inconsistent. So again, same thing. I'm going to take the first equation, solve it for y, so I can put it in slope-intercept form, and I get this, right? Minus 9x from both sides, divide both sides by negative 6. And then take the second equation. I would subtract 6x from both sides, divide both sides by negative 4. Gives me this equation. So now I have my two equations. Now, if you notice, after simplifying each one, they actually give me the exact same equation. Well, if they give me the exact same equation, they're going to make the exact same line. So that means every single point on one line would also be a solution for every single point on the other line. So this would be an example of when you have the same lines, you have an infinite number of solutions. Now, since it does have a solution and there's infinitely many of them, this is what's known as consistent and dependent. Okay, so the system is consistent and dependent because it has infinitely many solutions because the two equations are exactly the same, which means the two lines are exactly the same. So another example. So what happens if you have parallel lines? Well, let's look, if you're asked to graph a system of equations, again, here's my two equations. Again, if I were to graph them, I'm going to go ahead and take each one, solve it for y to put it in slope-intercept form, right? Subtract 3x from both sides, divide both sides by 4, gives me this. Take the second equation, right? Subtract 6x from both sides, divide both sides by 8, gives me this equation. And so now that I have my two equations in slope-intercept form, I could put them on a graph. Here's what I notice. And again, if you notice, look at their slopes. They're exactly the same. They have different y-intercepts, right? So it puts them in different places, but they have the same slope, which means they're going to go in the same direction, which means they're never going to touch. So if they never intersect and never touch, there is no x and y coordinate that's going to work for both equations. So therefore, since the lines do not intersect, their graph are parallel lines, so there is no solution that satisfies both equations. This system is inconsistent, okay? So inconsistent is when you have two lines that never touch because they're parallel. So therefore, there is no solution. All right, thank you guys for watching, and I'll see you